Welcome to Calculus.
Our stress tolerance level has risen so high that nothing phases us.
On this episode, Stevenson will demonstrate
In this example, you're going to notice that the structure of how this is worded is different than what we've seen. But our approaches are still going to be the same. So it says, find the area of the region R in the first quadrant that is bounded above by y equals radical x and below by the x-axis in the line y equals x minus 2. All right, well, if something's bounded above, what that means is the upper bound or the upper border of your area is going to be that function. If it says bounded below, that means the lower border or the lower bound of your function is whatever it's telling us. Now, it's telling us it's two different things. So let's draw a picture and try to make sense of this. First thing I notice is we have a square root function. Now that's a parent function we studied last year. It looks something like that. Now it says it's the region, the area of the region, in the first quadrant, so we're only focusing on here. It's bounded below by the x-axis. Well, that's the x-axis, but it also gives us this other line. Now this is a linear function. Its y-intercept is -2, so that's down here somewhere. And then it has a +1 slope. So I'm going to draw it like that. Now let's read this again. It wants the area of the region that's in the first quadrant only, that's bounded above by this and below by the x-axis and this line here. So here's the question. Do I use that area right here? The answer is no, because it wants the area in the first quadrant only. It's bounded below by the x-axis, see? And below by that line. Okay, so let's set up our problem. So it wants this whole region. So we know it's going to start at 0, so we need to know this point of intersection. I also need to know what is this point of intersection. So that's when the line is crossing the x-axis. So I'm going to figure that out as well. So scratch work over here. I got two answers for making these equal. So only one is going to apply though. So one of these has got to be extraneous. If we look at our sketch though, 4 is the logical conclusion here. And the reason I know that is because if I put 1 in, it's going to be somewhere over here between 0 and 2, right? Because I figured out that's the x-intercept for the line. But they don't even come together at all. So 1 is extraneous. So 4 is our answer. Now we're going to go ahead and try to find our area. But something should stick out to you. We have a problem. If I draw a rectangle here, and I draw a rectangle over here, they're using different sets of functions here. So what this means is I have to actually break this up into two separate integrals. We've seen this before, so we're going to partition this area right here. So we're going to call this area 1, and then this one's going to be area 2. So let's start with area 1. So area 1 is the integral from 0 to 2. Now, if you notice this is just the area of the function in the x-axis. That's something we've spent lots of practice on. So we're not using our fancy new formula at all. It's literally just the integral of radical x dx. Now let's look at area 2. Now area 2 is where we're going to have to use our fancy new setup. So essentially what we have to do is we have to take the uppermost function, so that's radical x, and subtract the lower function, which in this case is the line. And from there, we're going to do our get our answer for the area, and then we have to add these together. Now, my bounds are wrong though. My bounds need to be from 2 to 4. So don't make that mistake I just did. So remember, the first area is from 0 to 2. The second area is going to be from 2 to 4. We add those together, and then we get the total area. So now I'm going to work this out by hand here. Now I'm going to take my answer from the area 2, so from this interval, and combine it with the area from the first interval.